Hello everyone, welcome back. In this video, we will do some problems on the laser power and a number of photons emitted from the laser. Let us start. Here is the problem. A red semiconductor laser diode emits a light at a wavelength of 650 nanometers with a continuous output power of 5 milliwatts. Calculate the number of photons emitted by the laser per second. Right here they are giving you a laser which is emitting at a wavelength 650 nanometers, and the power of the laser is 5 milliwatts. We need to find out the energy of the photons and also the number of photons emitted from this for laser per second. Right, number of photons emitted from this laser per second. How many number of photons are emitting from the laser source for every second? That is the question that we need to do. Right, let us start. This is the valency band and this is the conduction band, and the difference between the valency band and conduction band is band gap, and you can write this is E2 minus E1, right? This is the E2 higher energy, this is the E1 lower energy, this is H nu, right? We can rewrite this H nu by Hc by lambda. But here the emitted, whenever electron is de-exciting from higher energy level to lower energy level, it is emitting a photon. The photon value is 650 nanometers. Right, 659. That means here lambda was given. Right, now what is the formula for the Eg? Eg is equal to Hc by lambda. We know H is a Planck's constant, C is a Planck's constant, C is the velocity of light, that is also constant. Lambda was given, so we can find what is the band gap. Let's start. So the power is given value. The power of the laser output is. So before that, I just wanted to remind you, whenever electron is de-exciting from higher energy level to lower energy level, after their lifetime, the photon will release spontaneously. However, in the laser source, when electron is in the higher energy state, before completing their lifetime, if there is another photon stimulating this electron to de-excite before their lifetime, there will be two photons will be released. Right? This is the first photon. As it is, that photon will come, and another photon will come from higher energy level to lower energy level whenever electron is de-exciting. These two photons will travel in the same direction and are in coherence with each other. So this is the stimulated emission, right? Stimulated emission. Right? This kind of stimulated emission, many times if it is oscillating between the resonator means our semiconductor ends are polished. This is the polished, this side is 100% polished, and this side is a 99% polished. Now these two photons back and forth it oscillates, and further some more electrons will be de-excited stimulatedly, which results enhancement in the stimulated emission. That stimulated emission radiation is emitted in the form of laser light. Right? So I hope you understand this. Now let us start doing our problem. Given information is the power is P is equal to 5 milliwatts. 5 milliwatts means we need to convert this into 5 into 10 power minus 3. What means you can write joule per second. Right? Energy per time. Energy per time. What means? So joule per second. And wavelength is given 650 nanometers. So you convert this also 650 into 10 power minus 9 meter, because 1 nanometer is equal to 10 power minus 9 nanometers. And the Planck's constant we already know, 6.625 into 10 power minus 34 joule second. This is the standard value, and the velocity of light is 3 into 10 power 8 meter per second. Now let's find out the energy of the photons. They have given you wavelength. Now we have to find out energy. So the energy of the photons is E is equal to H nu. Just now we have seen E here is the Eg is a band gap, H nu, which we can write Hc by lambda. Now substitute Hc, lambda, everything, we get the energy in the joules. Right? So H is a 6.625 into 10 power minus 34 joule second. The velocity of light 3 into 10 power 8 meter per second, and the wavelength is 615 to 10 power minus 9 meters. Now you can see here this second cancel, this meter cancel, the rest is the joules is left. So energy here your band gap energy is joules. Here a band gap energy is simply the energy of the photon, because electron is jumping from higher energy level to lower energy level with the energy which is equal to band gap energy, that is Eg is equal to E2 minus E1, right? So here this band gap energy is simply equal to your photon energy. So now let us simplify this. When you simplify, we always have to do numerator separately, denominator separately to avoid the confusion. So multiply these two, which gives you 1.9878 in 10 power minus 25, and actually here it is 19.87 into 10 power minus 26, but this was actually adjusted to 10 power minus 25. Now 650 by 650 nanometers. Now you further simplify this one, you get approximately 3.058 into 10 power minus 19 joules. This is the joules. This is in joules. If you want to convert this into electron volts, you need to divide this by 1.6 into 10 power minus 19 electron volts. That will give you electron volts answer. This is the energy of the photon in the joules. But if you wanted to write this in the electron volt, E is equal to 3.058 into 10 power minus 19 by 1.6 into 10 power minus 19. This will give you electron volt. Now you cancel this one. Now if you calculate this one, approximately 1.9 electron volt. This value will be in the electron volts. This will be in the joules. Both are same. Now let us calculate the number of photons emitted per second, right? So the number of photons emitted per second from the laser source is, the formula here is n is the number of photons per second, the total power by total energy. This is the power by energy. E is the energy, just now we calculated. We know already power, we know energy, so substitute this, right? We know power is 5 milliwatts, so 5 into 10 power minus 3, and energy is 3.058 into 10 power minus 19. Now you calculate this, simplify this, it will be 1.635 10 power 16. So that means for every second the laser emits approximately 1.64 into 10 power 16 photons per second. So imagine for 5 milliwatts the number of photons are this much. If you consider, if you increase the power, then imagine how many number of photons are emitting for every second, right? So this is how you can calculate number of photons emitted per second for a laser. I hope you understand this. If it is useful for you, you can comment in the comment section. Thank you. See you again in the next video.